Section 3.3, projectile motion. This is where it all comes together. We can look at our equations of kinematics in 2 dimensions with a very specific scenario that is often applicable to here on Earth. That if an object is under the influence of gravity alone and near the surface of the Earth, basically if it's flying through the air, if it doesn't have anything pushing on it, like not a spaceship example here, but if you're throwing something through the air, we know that the acceleration is only going to be downwards by this negative 9.8 meters per second squared. So this is only in the y direction that we feel this acceleration. In the x direction, assuming that there's no air resistance, which is what we'll assume for this semester, just makes your life much easier. In the acceleration, the x direction is always 0. There is no acceleration. These are 2 pieces of information that you can fill in your table every time you have something that is flying through the air. It's great. So make note of this. As a result of this acceleration, the x direction being equal to 0, that means once something is flying through the air, which is all that we will be focusing on here, the final velocity in the x direction must be equal to the initial velocity in the x direction. In other words, it must be a constant. This is another really interesting side effect with projectile motion, that the horizontal velocity will remain constant even as the y component is changing. So let's try this out with an example other than me throwing a tennis ball and knocking things over. All right, so example 4 here, velocity of the care package. An airplane is flying horizontally with a constant velocity 115 meters per second and an altitude of 1050 meters. The plane releases a care package that falls to the ground. Ignoring air resistance, A, how long is the care package in the air? And B, what are the magnitude and direction, the final velocity of it? All right. So we have a bit of a picture here where the airplane releases a care package. And here's our first piece of implicit information. When the airplane releases that care package is going to have the same velocity as the airplane. For just that brief instant when it's first released, right? When it's first released, we know that it'll be traveling the same way that it was while it was attached to the airplane. So I want you to take a moment to try to fill this in, and then I'll talk it through in just a bit. So go ahead and pause. All right. So first off, we want to immediately go to our acceleration and fill that in, right? We know the acceleration in the x is 0. In the y, it's going to be our negative 9.80 meters per second squared. All right. Similarly, I mentioned that the velocity is the same as that of the airplane at the moment it's released. That means if the airplane is flying horizontally with this constant velocity of 115 meters per second, that means all of that velocity is in the x direction. We have 115 meters per second going purely horizontally. And similarly, we have 0 in the vertical direction of velocity initially. For a brief instant, that package is just hovering there. As gravity pulls it down, it begins to move faster and faster down toward the ground. All right, so here are some good numbers that we've already filled in. Fix that 115 a little. We also know from the previous slide, since the acceleration in the x direction is 0, we can even fill in the final velocity here in the x direction, 115 meters per second. Sweet. There's one more piece of information here, and that's that we have this altitude of 1,050 meters above the ground, and we're interested in how long it takes the package to reach the ground. So that means our displacement is going to have that magnitude of 1050 meters. Now, we have to pay attention. Is this a positive or a negative displacement? In other words, in the y direction specifically, has the package gone in the positive y or the negative y direction? Since it's fallen down, this is the negative y direction. Even as it is moving in the positive x direction, it would be some positive displacement there. So this is really solid. We could fill in what we're looking for in part A. Part A says how long is it in the air? And so that's going to be tied to our time. All right, so as we're thinking about our time, we can think about our x and our y direction. Which direction is going to limit how long the care package is in the air? Is it going to be something in the horizontal direction that limits it, or is it going to be something in the y direction? Well, as we think this through, it comes down to when it hits the ground, that vertical direction that limits how long the care package is in the air. If it wasn't for the ground, the care package would keep falling. And it's not like it hits a wall, where if it hit a wall, then it would be the x direction that's limiting how long it's in the air. So with that in mind, I'm going to suggest we use the y direction to solve for the time. So let's go on to the next slide. I'm going to clear these pictures, but we'll have the information filled in very nicely here in neater writing than my own. So rather than using the x, let's look at the y direction. We want an equation that does not have final velocity. So our simplest approach there is going to be our y is equal to the initial velocity in the y direction. I'm going to write out these subscripts even though it's a pain because it's so easy to mix up my variables and I don't want to mix up any variables. So plus 1/2 a sub y, not just any acceleration, but acceleration in the y direction times the time squared. Now this is an equation that when you're solving for time is sometimes a pain because sometimes we have to use the quadratic as we saw last chapter. Here we have a benefit, and that is that the initial velocity in the y direction is in fact 0. Because that is 0, we were able to say, hey, this whole term is going to be 0. So that is huge. That makes our life much easier. Now when we go to solve this, we just have that the displacement in y is equal to 1/2 a sub y times time squared. So we can multiply by 2 and divide by ay, and we would have 2 times y, divided by the acceleration in the y direction is equal to the time squared. And we can take the square root of that time. Whenever we take a square root, we know there's a plus or minus out in front, but with time, we'll typically take the positive root. With velocity, we do care if it's positive or negative. And so we can then plug and chug here with our displacement and our acceleration. These are both negative, so they would cancel out underneath the square root, which is good. If we had missed that one of these was in the negative direction, our calculators would be very unhappy with us if we tried to take the square root of a negative. But as it is, we've taken the square root, so that square goes away. And you should be able to get that the time is in fact 14.6 seconds. Now, what if we had tried to use the x direction? Well, in the x direction, we don't know anything about the displacement. That's missing. So we need an equation that doesn't have the displacement. And so we could do that with our v final in the x direction is equal to v initial in the x direction plus the acceleration in the x direction times time. But the problem here is the acceleration in the x direction is 0. And so this whole second term disappears and we're left with just our same expression that we already knew, that our final velocity is equal to our initial velocity in the x direction. Doesn't actually tell us much, which is why in this instance we need to use the y direction to get the time. In other instances we might have used the x instead, but we didn't have enough information there. Maybe if they gave us that x displacement, then we could have done it. All right, so we now have filled in the time, that is 14.6 seconds, and we can now solve for the final velocity. We can note that we already have the final velocity in the x direction, right? We have this horizontal component of the velocity that has stayed the same throughout. We just need to find how fast it's falling straight down, and then we can combine the horizontal velocity with the vertical velocity to get the overall velocity, which is shown very nicely here. So if we want to solve for this final velocity in the y direction, the simplest equation for that is just using the time itself. So final velocity in y is the initial velocity in y plus however much acceleration in the y direction plus however much time has passed. Initial velocity in y is 0, so it's just negative 9.8, our acceleration in the y, times 14.6 seconds. So when you multiply that out, you get negative 143 meters per second. Why is this negative? Well, because in the y direction, it's going in the negative direction. It's going down. The x direction is going in the positive direction. So that's positive 115 meters per second. Now, if we want to combine this 115 meters per second with the v sub y, negative 143, that's where we can use our Pythagorean theorem, make a nice triangle here, and get that the final overall speed, or the magnitude of the velocity, is going to be the square root of each of those components squared, which comes out to 184 meters per second, once you have accounted for 3 significant figures in this problem. To get the direction, that's going to be the angle theta, and you can do it with, once again, this is an equation that keeps popping up a lot. So these 2 equations actually are really useful. I would put them on your note sheet because they just keep popping up. That we can find the angle with the inverse tangent of v sub y, the y component of the final velocity, divided by the x component of the final velocity. So when we plug in those numbers, keeping that negative sign, you'll get a negative 51.2. What does it mean that the angle is negative? That's telling you that relative to the positive x-axis, it is in the negative direction. So it is going slightly down, which matches our expectation and our understanding. So there we have our final velocity in magnitude and direction. Awesome. Now I want us to look at a conceptual example with 2 ways to throw a stone. So from the top of a cliff, a person throws 2 stones. The stones have identical initial speeds, but stone 1 is thrown downward at some angle above the horizontal, or thrown upward at some angle above the horizontal, and stone 2 is thrown at the same angle below the horizontal. Neglecting air resistance, which stone, if either, strikes the water with greater velocity? So we have one that's thrown downward, another that's thrown upward, both at the same angle relative to the horizontal. So I want you to think through this for a moment. What do you think is the case here? You can go ahead and pause. I encourage you to reflect for a bit. I'm going to offer just a little more that might help. This is a fuller picture. So if you want to reflect before you hear the answer, go ahead and pause now. All right, notice path 2, where it's thrown above the horizontal. The initial velocity creates this parabolic path, and at point P, because the horizontal velocity has stayed the same, and the vertical velocity has just inverted to be going down instead of up, point P has exactly the same velocity in the x and the y direction as it did for the initial case of stone 1. This is amazing, right? This is a fact of symmetry, and it only happens if you can throw them with the same velocity, the same relative angle of either up or down slightly. But as a result, it means that both stones will strike the water with the same velocity. Not at the same time, right? The one that we've thrown upward is going to have more hang time before it hits the water. But it will hit the water with that same amount of velocity. Okay. If you have questions on that, I encourage you to keep wrestling with it. Please ask them in office hours or stem cell or on the discussion board. One more example. I shot a bullet in the air. So suppose you're driving a convertible with the top down. Car is moving to the right at a constant velocity. You point a rifle straight up into the air and fire it. In the absence of air resistance, where would the bullet land? Behind you, ahead of you, or in the barrel of the rifle? So I'd like for you to reflect on this, see if you can come up with an answer. So I'm going to include a link to the video that shows this demonstration being done a little less dramatically, not with a rifle, but come up with an answer before you watch the next video.